All right, hello and welcome to the review. I'm just going to go over a few different things, a bunch of little topics, and hopefully they are useful for you. Of course, I can't go over everything, but hopefully some of these things you'll notice like, oh yeah, I need to go and review that some more. And that will be kind of the point, okay? To show you what you are good at and show you what you still need to review some more. Okay. So let's get right on into it. We'll just go in order, I guess, of logic, then proofs. So we'll take as long as we need to take. I've just made a bunch of little questions. I've taken a bunch from the book that we haven't done. Okay, so the first thing is write a truth table. So we need to remember our logical operations, and or, and not, and all those things. And it also appears that my, oh no, my tablet doesn't look right. It's not working correctly. So I'll restart my computer and I will be right back. Okay, now I have a tablet that makes pretty lines. Let's get started. So let's write a truth table for R, or, P, and not Q. So let's remember all those things. And so we have a bunch of different little options here. We have R's and P's and Q's, and so we need 2 to the 3 rows in our truth table. Oh man. So let's just get started, because we're going to have to write them all out. We have R and P and Q, and if you remember the trick, it's always true, false, true, false, true, false, true, false. This one alternates. I guess the order doesn't really matter, but this is the standard order. And this one goes true, true, false, false. It alternates twice, or half as much. True, true, false, false. And then we alternate half as much as that column, or that row. True, 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 false, 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 false. Okay, so that's R and P and Q. And now let's combine all these things. We have a not Q, and that will need to be anded. So let's do not Q. False, true, false, true, false, true. It's very much a pain when there are more than 2 propositional variables, isn't it? Then we have P and not Q, so we're going to and together these 2 columns. Okay, so P and not Q, and that's almost all the way there. P and not Q, well, one of them's false, so the whole thing's false. Ooh, true. False, 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 true, false, false. Okay, so we got 2 trues here. Let's see if we can make more trues, because now we're ORing things together. Let's OR what we just made with R. R or P and not Q. So all these things down here, R is false. So we just kind of move over whatever those were because we can't change them. So these are definitely false, true, false, false. And now these are all going to become true, even if they weren't before. Okay? So we got true, 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 true. And unless I made a silly mistake, that is the answer. Okay, so R or P and not Q under these values for R, P, and Q, it's apparently true. For these values, it's also apparently true, and all these 4 down here, the other ones, all these other 3, this one makes it false. Okay, so that is our final answer, and that is the truth table. Okay, hopefully it's all coming back to you now. All right, that's going from a truth table, or going from a proposition to a truth table. Let's go backwards now. So here is a badly drawn truth table. Here's P, Q, and question mark. What is question mark? What should that be? Well, if you remember my secret, you just pick out which of the lines make it true. So okay, it's true when this is true, and it's also true when this is true. So both of those are ways to make the whole thing true. The others make it false. Okay? So the way you can come about this is to say, okay, my proposition, my mystery proposition is true when P is true and Q is false. You see that? That's how you say it's true that Q is false. You say not Q. All right? And then continuing, well, it's true when this is true, or we're in this column, and P is, or we're in this row, P is false, so not P is true, and Q is true. Okay, so that, it could probably be simplified maybe. Oops. It is what the question mark is, okay? And this is one I might have already given you, isn't it? Isn't this exclusive OR? Yeah. So it really is exclusive OR, but who cares? We found one. And this way always works. Okay, so that's how you can go from a truth table to the real proposition. And you can also do it backwards by looking at the false ones. Sometimes that's easier, and then you just negate the whole thing. Okay, so that's that. Let's keep going. More truth tables, but now we're talking about equivalence. Okay, so let's write a truth table to figure out if this and this are logically equivalent. And that means, remember, their truth tables have the exact same values in each column. And by column, I mean row, don't I? Okay, so let's keep going. Well, we're going to have to put all these together, and let's go a bit faster maybe. Let's see if we can. P and Q, that's nice, there's only two of them. That makes me happy. True, false, true, false, true, true, false, false. Alright, and then P implies Q, we remember that. That is true, false, true, true. And then, okay, the other one is P and P implies Q. And we're trying to see, hey, are they logically equivalent or not? Maybe they are, maybe they aren't. P and P implies Q. So, what are these? We just have to and whatever this is with P itself. So, unfortunately, these are all going to become false. And so, if they weren't already, and they weren't already, so that kind of solves the problem already. But let's do it all. Let's finish it off. P and yes. And these are false then. So it's only ever true, apparently, when P is true and P implies Q is true. That's the only time they're both true. The rest of these, we have no dice. Okay, so are these the same? Well, some of them, yes. These ones, but not these ones. Okay, so the answer is no. Not logically equivalent. Okay, and that would be the answer. Alright, so hopefully this is all making sense. Please come yell at me. If it's not, there will be Wednesday office hours at least, so you can yell at me and ask me questions right before the midterm. Okay, let's prove that this is a tautology using the laws of propositional logic. So remember that a tautology is just this becomes true. It's always true no matter what, apparently, R and P are. Okay, that is the idea. And so we're going to use the laws of propositional logic to get ourselves there. And here is the table that I have reopened up. So let's use this. Let's use this to make all this all work out. All right, so this is what we start with, not R, or not R implies P. So that's what we start with. And then we have to whittle this all the way down to true eventually. Let's get there. Okay, so the first thing that usually you'd always want to do is to like break down everything into the simpler pieces. So like get rid of the implication, make it just nots and ands and ors and all that stuff. Okay, so when you have an implication, that is equivalent to, where is it? Down here, this conditional identity. So P implies Q is the same as not P or Q. Okay, so we have to be very, very silly about it. So we have to say not R, and then or P. Okay, so that's that. And now we can break this down. That's something we can definitely do. It's not R. That just makes positive R, true R. not R or P, and we should definitely say what we're doing as well. So we first use the conditional identity, cond ID, then we use double negation. That's exactly what it's called, which is nice. Double negation. And now, ooh, I have a not R and a yes R, so I can bring those together if only it looked like that, and I can use my associative law of OR to bring those around, okay? Not R or R. That can be in parentheses, and the P can be all alone. That is associative law for OR. And, all right, now this, that we can get rid of, okay? Because we have a false thing and a true thing. So where is that? Where is that? That becomes just true. Okay, okay. Are you ready? Are you ready? But it's in the wrong order, darn. So we can swap them around using the commutative law for OR. So let's get there. We have R or, not R, still in parentheses, or P. I'm going to try and make it smaller. This is the commutative law. Commutative law for OR. And now we can make this true because they all match up. That's true or P. That is, what's the name of that law? That is the complement law involving OR. I'll just call it comp law. And then true or anything is always true. Where's that rule? Is that the domination rule? Yeah. Oh man, but the true's on the right. Are you kidding me? So let's use commutativity just to spell it out. Obviously, after this chapter, you never have to do this again. But it's good to know that all these rules exist. Like maybe, remember when you were learning like 2 plus 3 is the same as 3 plus 2? It wasn't obvious that those were commutative, but now we know, and now we know the same for OR, okay? And now we can finally use the domination law. True domination law. Okay, so we took this, we translated it into equivalent things, and we made our way down to true. And it's always true no matter what R and P are. You could fill out the truth table if you really wanted to. That might have been a bit faster, but we wanted to practice all of our laws. Okay, so that is that. Hopefully that's all working out for you. Okay, let's move on to quantifiers now. Let's bring those into the mix. And remember, quantifiers are just, okay, we're introducing variables, like for all x, or there exists a y, and then we can use that variable in the rest of our formula, okay? And variables also can introduce the idea of predicates on top of propositions, so propositions that need variables plugged in, propositional functions, if you will. So, okay, let's translate the following into quantified statements, okay? Maybe I should spell it like that. Subject-verb agreement. Okay, so the square of every number is at least 0. Okay, do try these yourselves. If I maybe didn't mention that before, it's very, very good practice to try this yourself. Okay, so the square of every number is at least 0. So I need a number, so let's call it n or something. And if I square n, it better be at least 0, so it better be greater than or equal to 0, right? Ooh, did we do it? So I need to introduce this n somehow. Is it just one n? Like, is it exists? There is an n that this is true for? Or no? No, it's every number. For every number, call it n, its squared is at least 0. It's greater than or equal to 0. Okay? I hope you see how at least translates to greater than or equal to, not just strictly greater than. So, and of course you can replace this n with anything. Could be q, could be p, could be whatever you want. But that is, I do believe, the answer. Okay? And then, okay, there is a number that is equal to its square. I think we know that one. That one's 1 or 0. What do we have? So, what's going on here? What do we do? What do you think? Definitely pause the video and try it. So we have a number that's equal to its square. So there's some number n, we have to introduce it somehow, and what's true about that n is, or let's use a different number, let's call it x this time. What's true about this x is that it's equal to its own square, so x is equal to itself squared, okay? And is this true for every x in the world, every possible number? I don't think so. I think it's only true for at least one. That's what it's trying to say. So there is a number. We don't know which one. Not all of the numbers have this property, but some do. At least one does. There exists an x such that that x is equal to its own square. X is equal to x squared. Okay? And again, you can replace all these variables with whatever name you'd prefer. Okay, so hopefully this is making some sense. It's all coming back to you. That is the key. That is the goal. All right. Moving on, moving on. Let's use De Morgan's law to push the negation inward. So here's the negation. It's way out here on this whole darn thing. Okay? It's as if we were negating this entire thing if we added extra parentheses for fun. Okay? So let's do this. So not for all x, p of x is true, and in parentheses, q of x is true, or r of x is true. 1, 2, 3. Okay. So this is equivalent to, if we push this negation this way, we have to, if we're going to put it right there, we have to flip-flop the for all to there exists, okay? Because remember that for all is equivalent to like a bunch of ands, right? It's something and something else and something else. It's you and together everything in your domain. Whereas there exists is equivalent to, okay, it's either this one or it's this one or it's this one for everything in your domain again, okay? So that's why they flip-flop. You're just essentially using De Morgan's law on every member of your domain, okay? So we're going to flip-flop that to there exists an x, and then we have the negation sitting here. P of x and q of x or r of x. And now if I want to bring this inside, we're going to have to do De Morgan for real. So this one's got to flip. Exists an x such that, okay, not p of x, or not of this whole thing, q of x, or r of x. And now, this one's kind of as far in as it can be. This one, though, we can do something about. We can bring it in one more time using De Morgan's law. Okay? There exists an x such that not p of x is true, or, in parentheses, not q of x is true, and not r of x is true. Okay? So, hopefully that's making some sense. That is as far as you can push these. They're right next to the predicates now, and hopefully I didn't make any silly mistakes. Sorry if I did, but I think you get the general idea of what this should be. This is what I hope the answer is, but if I made a silly mistake, I'm sure you saw it. Okay, so that is De Morgan's law for many things. Let's keep going. Translate the following to a statement with nested quantifiers. Oh, you remember these? You can double up on your for alls and your there exists. You can go even more if you'd like. It's just if you have multiple variables, they have to be introduced somehow, and you're going to need a quantifier for those. Okay, so here is the predicate. fxy is true if and only if. It's defined to be true if x is a friend of y. Okay, so it's going this way, like x is a friend of y. Okay, and we're going to assume that for any two people, either they're friends or they're enemies. So either it's true, it's like either x is a friend of y, so fxy is true, or they're an enemy, so x is an enemy of y, which is not fxy. Okay, that's how we'll interpret that. So do the first one. Try it. How do we represent everyone as a friend of everyone else? Okay, we have to say there are people, like there's a person x and a person y, and they're friends. And this is true for everybody, every x and every y. And I think I gave away the answer. For all x, for all y. And these could be in any order because they're both for alls. So introduce any x, any y, anybody anybody in the domain, which is, I assume, like a class or a family or something, or like a neighborhood. So for every x and for every y, that x is a friend of that y. And you can plug in anybody. Doesn't matter who. They're all friends of each other. Everyone is a friend of everyone. Okay? So, hopefully that makes sense. You double up on the for all. And then, okay, what about this one? Someone is a friend of someone else. All right? So again, now we have fxy, but it's only true that one person, at least one person, is a friend of someone. Okay? So someone, this x is a someone. We don't know who it is. It could be anybody, but it's not everyone. And that's again a there exists. Okay? When you have something that is only true for at least one thing, when you're introducing something that's not always true but is sometimes true, you use there exists. Okay? And so someone and someone twice, that's two there exists. Okay? There exists an x, a person x, and a person y, such that x is a friend of y. Okay? So we can instantiate x and y with real people, and this will be true for at least one of them. Okay? That's the idea. All right? Now these two are going to be fun because they're where we have opposite quantifiers, and I really, really encourage you to try this yourself right now. Someone is a friend of everyone. What does this mean? What order does this require? Okay? So there's somebody, and that someone is a friend of everyone. So you have to pick this one first. Okay? You have to choose your person, like, okay, you over there, you are a friend of everyone. So just someone, that's there exists. Okay? And that someone is a friend of everyone. So for every y, no matter who the y is, they're a friend. So for all y. Do you see that? Okay, hopefully that's making some sense. And this order is key because obviously this is the last possibility. The other way around is this one. It's not the same. Okay, everyone is a friend of someone. So every person in the world, doesn't matter who they are, so everybody gets a turn at being x. That x, instantiated to everybody, eventually, that x is a friend of somebody. So everybody has a friend, okay? Everyone is a friend of someone. So this y is not everyone, it's only certain people, a certain person perhaps. So it's for all x. There exists a y such that f x y is true, okay? So everyone, for all x, it's true that this inner part is true. It's true that for somebody called x, that there is somebody else, that's a y, who they're friends with. Okay? So I hope you see the key difference between these two. They are not the same. Okay? Those are not the same right there. Alright? Someone is a friend of everyone is not the same as everyone is a friend of someone. Okay? I hope you see that. Okay? Please yell at me if this is not making sense. This is a very important topic. Okay? Alright. Moving on now to arguments. Let's see how we're doing on time. Yes. So arguments, let's keep going. Arguments are when we want to say something and enforce the fact that it is true. Like, prove that we followed the rules of logic correctly and we are concluding something that actually makes sense. Okay, so your arguments always look like hypotheses and a conclusion. And it's true that if you assume the hypotheses, the conclusion must follow from them. Okay? That's what validity means. Validity means if the hypotheses are true, then the conclusion must always be true. Okay? So we're going to use a truth table to figure out whether or not this is a valid argument. And I think it's not a valid argument, it's trying to say, so let's make sure of that, and then also figure this out. This is kind of trying to use like modus tollens, and it's doing it wrong, okay? So that's why it should be invalid to prove it like this. So let's figure this out. It's saying that, okay, I know that P implies Q, and I have not P, so then I must have not Q, right? And that is an invalid argument, and let's find out why. So we got your P, we got your Q, true, false, false, true, false. And then we have P implies Q. That's true, false, true, true. And then we have not P. Okay, so we're assuming both of these, and then we're trying to prove not Q. So not P is, just negate this entire row, or sorry, column. I will forever get those words wrong. False, false, true, true. And then we have not Q, that's our conclusion. So let's write that as well. That's going to be false, true, false, true. And the idea is, okay, we go and find every row. Every row where these two are both true, okay? Because we're trying to prove that, okay, if the hypotheses are true, then the conclusion must be true. So where are all of these two true? Okay, it looks like in the last two columns. And by columns, I of course mean rows. So in the last two rows, we have they're being true there, and they're being true there. So we have to then notice that these are where the hypotheses are true. If this were a valid argument, it must imply that these are both true right here. This one has to be true, and this one has to be true. This one checks out, but this one does not. Okay? Not a valid argument because of this row. Oh, I got it right this time. This row ruins everything. Okay, so that's why it's not valid. It's not valid because, well, it's true. P and Q are true, and if P implies Q is true and not P is true, well, it's unfortunately not the case that not Q is also true, because it's very possible that Q could have been true. Okay, that's the idea. It's not under every case where this is true. Okay, doesn't always hold. So hopefully that makes sense to you. That is why this is not a valid argument. Okay, and now I think this is the longest proof. If I was looking at the answer in the book of this question, and it is a long one. So it's going to take a while. I'm probably going to have to make a new set of slides, or a new little slide for it. But it's going to be very helpful because it's going to combine a lot of things. Okay, so we're going to prove that this argument is valid. So it's apparently a valid argument, this one right here. And we want to prove it using inference rules. And those inference rules must have quantifiers. So the first thing that we need to do, though, is if we want to do a kind of proof, we have to find the form of the argument, which means we have to translate it from English to math. Okay? So this is the argument. These first two things we're assuming to be true, and then we're trying to prove that if those two assumptions always hold in every universe where these are true, this must also be true. Okay? So let's figure this out. And I, of course, encourage you to do this yourself. Hopefully you've already done that. You've paused the video, given it your best shot, and now we're going to do it together. Okay, so we're going to need some predicates, first of all, and then we'll find the form of this argument. So every student on the honor roll received an A. So it looks like we have some properties of students, okay? A student could be on the honor roll. They could also receive an A. So let's do h of x for h is on the honor roll, or sorry, x is on the honor roll. And then a of x is x received an A. Okay, no student who got detention received an A, so there's also d of x. X got detention. I hope you see how I'm figuring out that we have these kinds of properties, these kinds of predicates that exist on a student. It could be true or false for every student. X got detention. And then no student who got detention is on the honor roll. Okay, so it looks like we've done them all. We've got everybody, every kind of property that this is talking about. And I'll put these over here. So now I want to use these to find the form of the argument. So let's translate it over here with a big arrow maybe. So every student on the honor roll received an A. That is screaming for all, I hope you see. For all x, and it could be anything. So let's call it y over here. For all y, every student y, if that student was on the honor roll, then they received an A. Okay, do you see how I'm translating that? It is a bit of an art, but it should make sense. Every student who's on the honor roll received an A. So if you're on the honor roll, then you must have received an A. That's the idea. It's implication. All right. Then no student who got a detention received an A. No student. It's not true that there is any student who got a detention and also received an A. Okay? It's not true that there exists. Let's call it Z over here, because why not? There is no student Z who both got a detention and got an A. That poor student. Okay, that's unfortunate, but that is apparently what this translates to. I hope you see it. So that there exists. Oh, I'm sorry, it's not true that there exists a student such that they were in detention and got an A. Okay, I forgot the negation. That is very, very important. Okay, so hopefully you see how I'm translating that to this. That's very important. And then, okay, it's saying no student who got a detention is on the honor roll. Okay, so no student, there isn't anybody. There is not some student. It's not true that there is a, I don't know, W. There's no student W who got a detention and is also on the honor roll. Okay, therefore, no student who got a detention is on the honor roll. Okay, dun dun dun. There is no W who both got a detention and is on the honor roll. So there does not exist any student W who both got detention, or sorry, not Z anymore, D of W, and is on the honor roll, which is H of W. Okay, so here's the whole form of the argument. Now we need to prove it. Okay, we have taken away the English to pure math, and now it's our time to shine. This can be blank. Here we go. So this is what we're trying to prove. Let's make it a bit... No, it's never going to work, is it? Let's keep it there, I guess. And let's go from there. Okay, I am recording this as good. So the idea is we have to go and prove this. Oops. We have to use the rules of logic to prove that all this is valid. This is the therefore part. Let's add that back here as well. We have to somehow use this assumption and this assumption to prove this assumption. Okay? So let's go to the other slides and figure out how we can take apart something with quantifiers. Not that one. That one. Okay, so we need to prove, dun dun dun, it's not true there exists a W such that D of W and H of W is true. So remember this is equivalent to, if I go up here, equiv to for all W, and then we do the negation inside of both of these and flip the N to an OR. For all W, it's not true that D of W or H of W. So if we just went and proved this, that would imply this, okay? Because those are equivalent. So maybe that's the way forward. Okay, and now this is where it gets kind of painful. We have to eventually get this, yes, but there is a long walk before then. Okay, so let's get started. We have a few things that are hypotheses, and we're eventually going to need them. So let's just say these are our hypotheses. Like, all right, 1, for all y, h of y implies a of y. That's a hypothesis. Okay, hype. Then 2, it's not true that there exists a z such that d of z and a of z. That's a hypothesis. This is also negated there exists, so we might as well, let's confirm I'm actually recording, might as well use De Morgan's on this and just get it in a nice form to begin with. So, okay, this is for all z, not d of z or not a of z. Okay, so that is De Morgan's law on 2. De Morgan on 2. Okay, so now we have these things. And our goal, again, is essentially this one, because that'll lead to this. So we need to prove it for all. And now let's go to the slides over here. So we want to prove it for all. this one. So we need to pick an arbitrary element out of the domain. We need to pick an arbitrary student so that we can generalize over every student. Okay, so for, let's say that S is an arbitrary student. Arbitrary element of the domain, which I'm going to go ahead and assume is students in some school. Okay? And we're trying to do universal instantiation. Okay? This is universal generalization. So for all gen, part of it at least. So that's why we're introducing this. It's okay to do. All right. So because I have an arbitrary student at my disposal, I can plug that student in to this and this, because these two statements are supposed to be true for all y's, for all z's. So they're definitely true for my one s. Hey. So let's use this. Okay, so I know now, 5, that, and the reason you can do that again is, okay, I have an assumption, I have an element, then I can apply the for all and get the fact that that's true for that one thing. Okay, so we say h of s. I'm going to use this one now. H of s implies a of s. Okay? And we're getting that from universal instantiation. And I'll say for all inst over here. Okay, I have this. And we might as well get this one too. Why not? 6 is for all z. Well, definitely works for my s too then. It's not true that d of s or it's not true a of s. That's another for all instantiation. I guess we're using 4 and 1 for this one, and we're using 4 and 3 for this one. Okay, so these are the things that we know now, and hopefully we can use those to our advantage. Okay, so the trick is, from here, these are the two things that we know, we have to combine them somehow. The trick is usually get rid of implications, just make this all as simple as possible. So 7 is not h of s or a of s, so we're using the conditional identity. And now I have these two things. I have not d of s or not a of s, and I have not h of s or yes a of s. Okay, so true and false. There's something that can be done with those. If we go up here, dun dun dun, we can do what's known as resolution. So if I have the opposites with ors involved, and then I have two other things on the other side of those ors, I can bring those two things together. And you can go and prove this valid if you would like, but it's just saying that, okay, I don't know if either of these are true, but it doesn't really matter. I can pick these out. Okay? So it's kind of like making them go away somehow. All right? So let us use resolution on, you see how the A's match. And I'm going to assume that you understand that we can like flip-flop these using commutativity. So let's use resolution now on 6 and 7 to get, wait for it, we have, I guess, not d of s or not h of s. Yeah? And that should be the final answer. It should look something like, oh, I think I forgot something. When I push that way, and I did the negation, I needed to negate that and negate that one. Looks like I forgot to negate this one. Sorry about that. So now that you see, this looks a whole lot like this. Yeah? And we got this from resolution 6 and 7. Okay? So now, because s was an arbitrary element, bam, we know that this is true for s. It's true for any s. Oh man, 9. If I have enough room, I'm going to try. I'm sure going to try. I know now for all whatever I want to include, let's call it w, because why not? For all w, not d of w, or not h of w. Ho ho. And this is achieved from this, and S is an arbitrary student. And we're using this rule, the one that gives us the proof of a for all. We're using universal generalization and we're using it on 4 and 8. And now finally we have this because of De Morgan's law. Okay? So I guess we'll go over here. So 10 is, it's not true that there exists a w. D of w. Let's try and make this a bit more legible. D of w and h of w. And we got that one from 9 and De Morgan. Okay, and that's finally what we wanted. It's that QED. It's a valid argument. We've proved it. Technically, this is in the proofs chapter, but still QED. We got what we wanted. Bam. So hopefully that was fun. It took a long way, but we have practiced all of the ways that we can do many a thing, okay? We practice how to do universal stuff, how to prove a for all, which is very important. Because now that we're about to talk about proofs, that's going to become very, very useful. Let's make sure everything's being recorded still. Yes, yes, yes. So let's start with proofs now. So I have 4 examples, and they shouldn't be too bad, any of them, but they're going to show you the different ways to prove things. All right, and the ways that I want to highlight are direct proof, proof by contrapositive, and proof by contradiction. Okay? These are 3 separate kinds of proofs, and I want you to notice the difference. So with direct proof, what you're doing is your thing that you're trying to prove is always like some P implies Q, right? And the way that you're going to prove it is assume the hypothesis, assume P, and then try and prove the conclusion Q. Okay? That's how you can do direct proof, and we proved in class why that's valid. That's correct to do. That actually works. That's direct proof. Proof by contrapositive is also a form of direct proof, because what you do is assume the negation of the conclusion. So it's again, you're trying to prove P implies Q, something of that form. You assume not Q, and then you try and go and prove negation of the hypothesis, not P. This is just the contrapositive of the original implication, and we know that those are equivalent. Okay? The reason we can prove those like that is because they're equivalent, and this is now just okay, take the contrapositive and do direct proof on it. Assume this, prove that. Okay? That's sometimes very, very useful because negating things helps a lot. Okay? It might introduce some double negations, which make some very nice things happen for you. And then proof by contradiction is kind of the odd man out because it's not very similar to any of these. It is and it isn't. Okay? So proof by contradiction is who cares what your theorem looks like. It doesn't have to be an implication for all proof by contradiction cares. It could just be anything. It's like some long string of things with implications and ands and ors and nots. It doesn't matter at all. Just pretend that your theorem was T, or no, not T. Let's just pretend it was P. All you do is assume that P is not true. Assume your theorem, not P. All right, let's just call it THM is your theorem. You assume not theorem. And then you try and prove that false is true. You try and get to false. Because from false, you can get anywhere. False implies everything. False implies, I don't know, Q for all Q. That's true. Okay? False gets you anything you want. Remember your truth tables. It's not false or that. Always true. Okay? So that's proof by contradiction, and usually you're going to end up making false because you have 2 things. Like the thing that you assumed, you can kind of whittle that down to, okay, I have some not P. And then also, oh, if the universe were normal, I also have P. And then these together like create a horrible mess, and that is your contradiction. Okay? These can't both be true at the same time. Oops. That is your contradiction there. Okay. Yeah, you just prove that you have both. And that's, of course, equivalent to false. Okay, that's all I wanted to say now. Okay, so let's prove this first thing by direct proof. The average of two odd numbers is an integer. Okay, so we have two odd numbers, and we need to prove that the average of them is an integer. So we have something like, okay, we have two numbers, x and y. This should work for any of them. If they're both odd, so x is odd and y is odd, that should imply that their average, x plus y, over 2 is an integer. Okay, that's your theorem, and now you can see the implication involved. I hope you see that. Okay, so let's assume this. Assume, so proof. Assume x and y are both odd. So that means x equals 2k plus 1 for some k, and y equals 2, I don't know, j plus 1 for some j. That's the idea. K and j, who are integers, of course. Let's use this now. Let's plug those into what we're trying to get. We have to show that this is an integer itself, so there can't be any fractions left over. Okay, under this assumption, x plus y over 2 now is, well, let's plug in x. That's 2k plus 1 plus 2j plus 1 over 2. And look what we can do. That's 2k plus 2j plus 2 over 2, which equals k plus j plus 1, which is definitely an integer. It's the sum of integers. Okay, you can spell this out a bit more in a formal proof, of course, but you'll just say, okay, that is the final answer. K plus j plus 1 is equal to x plus y over 2, and k is an integer, and j is an integer, and 1 is an integer, and the sum of integers are still integers, of course. And that's what we wanted. QED. Okay, hopefully that wasn't too bad. So again, I hope you're trying this yourself. That's how you remember things. Okay, so let's prove the next thing by contrapositive. For every integer n, if 5n plus 3 is even, then n is odd. So we have something like, for every n, if 5n plus 3 is even, that implies that n is odd. And so we're going to prove this by contrapositive. So we're going to assume the negation of this and prove the negation of this. So assume n is even, prove 5n plus 3 is even. Interesting. Very, very interesting. It's odd. Prove it odd. That is what we want, so let's figure out how to make it happen. That is a 5, not an S. Okay, so proof. Assume n is even. That means n equals 2k for some k. All right, now that we have this, let's go and prove that 5n plus 3 is somehow even. However shall we do this? Okay, prove that it's odd. Why do I keep doing that? I'm sorry. I'm sure you're yelling at me through the screen right now. It's hard to be precise and also say things. Okay, so yes, the negation of this is n is even. Negation of this is 5n plus 3 is odd. Okay, so we're going to prove that this is odd. 5n plus 3 is odd now. So 5n plus 3 equals, plugging in for n, 2, let's see, 2k times 5, so 5 times 2k, I guess, plus 3. Okay, that is the idea. How can we simplify that? Well, that's 10k plus 3. That's still not very useful now, is it? Because this 3 is not a 1. We need to somehow make it a 1. And so here's the secret. It's silly, but this is the secret. We bring out a 1. We need a 1 by itself. So we do 10k plus 2 plus 1. That's the same, right? And then we can write our parentheses like this, and I think you can see you can take a 2 out of this. You see that? That's silly, but it's possible. That equals, this is not 10 to the k, the k is down here. 2 times 5k plus 1 plus 1. So it's 2 times some integer, that's an int, plus 1. And that's your requirement for it to be odd. So 5n plus 3 is odd, and that proves the original theorem because it was the contrapositive of it. Okay, that's a silly little trick. I admit that I had to look it up to remember it. Okay, so that's proof by contrapositive. And now one last one. Do not confuse proof by contrapositive with proof by contradiction. Okay, contradiction is assume the negation of the entire darn theorem. Okay, so if the product of two positive real numbers is larger than 400, then at least one of the two numbers is larger than 20. Okay, so what is the negation of that whole thing? Okay, so again, let's do this. So assume this is our proof. Assume that the product of positive real numbers, it's two positive real numbers, is larger than 400. So assume, I don't know, x and y, x times y for some x and y that are positive real numbers. X is greater than 0 and y is greater than 0. And their product is greater than 400. xy is greater than 400. Okay? And one last time, assume that something's wrong here. Assume that, well, we would like at least one of the two numbers is larger than 20. Let's assume the opposite now. That's for contradiction. And both of those numbers, and x and y, are both smaller than 20. Sorry about all these ands. I hope you understand what I'm trying to do here. This is the part where it makes it the opposite. Okay? So assume you have all of these beautiful things, and then also the negation of that last thing that you expected. Okay? So that's the negation of the whole thing. Dun, dun, dun. It's because, like, if you have P implies Q, that's essentially what this is. It's a very long implication. The negation of that, remember, it's equivalent to not P and, P and not Q. So I'm assuming all of the normal stuff, and then that last thing, that last conclusion, that's what I'm negating. So assume all this stuff is beautiful, and then also the negation of the conclusion. So the then part after that, that's something I'm negating. So negate this. Hopefully that makes sense. Please yell at me if it does not. And you know what? I am sorry because the opposite of larger than is less than or equal to. Boop, boop, I am so sorry. Okay, so we can use this now to our advantage. Assuming all these things, we need to somehow derive a contradiction. So, let's see here. We have, I think, these two that we can somehow multiply together. I think that is the right way forward. So, let's say, I don't know, we have this one. Let's take that and multiply it by y on both sides. So you can totally do that. X is less than or equal to 20. If we multiply that by y on both sides, we get xy is less than or equal to 20y. That's useful. And then we can multiply this by 20, because then we can have 20y on the left and something else on the right. So with that, we also have y is less than or equal to 20. We can get from that, by multiplying both sides by 20, 20y is less than or equal to 400. Yeah? So putting these two together, I can combine them now. So that one and then that one together, that makes that is less than that, and oh yeah, that's the same thing, is less than that. It implies now we have xy less than or equal to 400. Ooh, and there's the contradiction. Do you see it? So if this is like, I don't know, this is like 2, and this is like 1, we're assuming this. And we just show that this also has to be true. 1 and 2 make a contradiction. 1 and 2 is equivalent to false. Contradiction. which implies the theorem. Okay, so that was a fun one. Some fancy math had to be used, but hopefully the idea makes sense. You're going to negate the entire theorem and then try and find a contradiction. Somewhere where the universe doesn't make any more sense. Okay? And then finally, let's do a proof by cases, and that will be everything. I'm sorry if this went long, but you're not required to watch this, I guess, is the idea. This is all for you anyway. Okay, let's prove by cases that for any real number x, the absolute value of x greater than equal to x, and absolute value of x is greater than or equal to negative x. Okay, so the absolute value is going to require something's either negative or non-negative. Yeah, I think that's going to be our two cases most likely. So let x be a real number. So case 1, x is greater than or equal to 0, and then case 2, x is less than or equal to 0. Okay, so we're going to have to prove both of these cases, and then that covers x. And oops, I mean strictly less than for this other case. That's the opposite. Okay, and both of these together, if we prove any x that's it's true when it's greater than or equal to 0, and we prove that it's true when it's strictly less than 0, then we've proven it for every possible value that x could be. Okay, that's a number sign. All right, so if x is greater than or equal to 0, let's start. So x, the absolute value of x, if x is greater than or equal to 0, just following the definition of absolute value, well, it's going to be equal to x. Yeah? Which is absolutely true that it is greater than or equal to x. Okay, x is greater than or equal to itself, for sure. That's fine, so check for that. We also need to prove this. Absolute value of x is greater than or equal to negative x. And let's make that work. So absolute value of x is, let's see here, equal to x, but x is greater than or equal to 0. And that implies that this is true. Because we know this, we also can know that, well, if x is greater than or equal to 0, that means, if you negate both sides, negative x is less than or equal to 0. And this is the absolute value of x. It's greater than or equal to 0. Here's its less than sign. We can take this, and these two sides match, and this, which is equal to the absolute value of x. Okay, hopefully you can see how I'm putting together these two things, these kind of chain together, to get negative x is less than or equal to absolute value of x, which is this, just the other way around. Okay, so that is the other side, proof. Okay, that is case 1. Let's do case 2. So x is less than 0. That means that the absolute value of x is equal to negative x. Okay, that is what needs to happen. And negative x is going to be greater than 0. Okay, and we know that because of this. If you take x less than 0, negate both sides, you get negative x is greater than 0. Dun dun dun. And so we have that, and then also x is less than 0, so we can again chain these together, where we've got x, and then 0, and then negative x, which is equal to the absolute value. All those together again. I hope you see it. I'm kind of chaining them. Let me show you exactly. Let me spell it out. So we have, let's see here, x less than 0, then we have 0 is less than negative x, which is equal to the absolute value of x in this case, because we have to negate it when it's negative. So this is less than 0, but 0 is less than this. So bring both of these together, we combine those into x is less than absolute value of x. And so, of course, it's also less than or equal to, okay? Which implies x is less than or equal to absolute value of x, which is what we needed. That's the first part. Check. Okay, let's talk about this one. Absolute value of x is greater than or equal to negative x. Well, it's actually equal to it, so this is useful. So absolute value of x is equal to negative x in this case, just by the definition of the absolute value function, if you go and look that up, which is definitely greater than or equal to negative x, because it's equal to. Okay, so that absolute value of x greater than or equal to negative x. Check. So we proved this and this for both cases. This is a bit weird trying to remember how to do inequality stuff, but hopefully it's all coming back to you. So QED, and that is everything I have for you. So the midterm is going to be multiple choice, but this was all the stuff that might appear on it. I'm sure there's more that I left out, and I'm sorry, but this was all the meat that I tried to get for you. Hopefully you have seen some things that you need to go and brush up on, or you are extra confident now that you are remembering all of this stuff. Okay, so yeah, please yell at me if you have any questions. There's going to be an office hours before the midterm, and do try to take it during my office hours so that I can be there and answer any questions that you have. Okay, so that is the midterm review. Thank you for watching if you got this far. Hopefully you just like skipped around or something. I will see you on your midterm day.